Murray Holland from University of Colorado Boulder here. Murray is a professor of physics at UC Boulder and a Gila Fellow. Murray is from New Zealand, where he did his bachelor's and master's in math. And he already caught the quantum optics bug early. So his master's thesis was on quantum non-demolition measurements. He then did his PhD in Oxford, where he was the Rutherford Scholar, and he worked on quantum enhanced interferometry during his PhD. And after his PhD, he moved to Boulder as a postdoc in 1994, and he has since been in Boulder as a faculty member since 1996. Murray works on an amazing range of topics in quantum optics, quantum information science, cold atomic gases, and he's also one of those superhumans who do both theory and experiments. So we are very lucky to have Murray here as our speaker for Colloquium today. So with that, please welcome.
Right, thank you very much for that nice introduction, and great to be here. It's been a long time, actually. I'm not sure why, but it's great to be back, and really enjoyed all the discussions today. So thanks for everybody that's participated. And I'm going to talk a little bit about some theory and experiments that we've been doing in Gila over really the last few years, probably going back about 5 years, but most of what I'm going to talk about is an experiment that we've built up since last August. So actually, this is very, very new stuff. And I'm going to begin a little bit by just telling you a little bit about the motivation for this and what our Quantum Pathway Institute is and what that's to do with. And it's sort of motivated by an effort that's going on in NASA to try to do remote sensing of planet Earth with satellites. Of course, this is work that's been going on for many, many years. In particular, this is actually, it looks a bit weird on the screen, slightly better in the original, but it gives you a map of planet Earth. There are a number of contributions that come into the gravity field that surround our planet. And these have been measured by, in particular, by two very, very sensitive classical accelerometer-based systems, Grace and Gochi, and I'll show you a little bit more about that in a sec. But these are kind of the gravity fields, and they're measured in these strange units, milligals. It's a sort of CGS unit. Gal comes from Galileo. But just to show you the general idea, the Earth is not a sphere. And in fact, 9.8 that we always quote varies quite a lot across the planet. It's actually more of an oblate spheroid, so there are some distances which are further away from the center. So you get different values for G as you move from the equator to the pole. And these things down here are measured in these milligal units, and these sort of hundreds of milligal. Now, so what is this wacky unit? Well, if you want to remember, 1 milligal is 10 to the minus 5 meters per second. But basically, it's a micro G, if you like, so a millionth of the actual base value of G, which we'll use in this. So the fourth or fifth decimal places vary based on the fact that the Earth's not a sphere. And so these things are being measured, I mentioned, by these two kinds of satellites. This didn't operate for very, very long. Grace has been going on sort of in various stages, Grace follow-on, Grace 3, and so on. This is basically the state of the art. You've got two satellites whipping around the Earth, and they use laser ranging between them to measure the distance between them very, very accurately. And so as they go through the gravity field, they catch up or slow down, and you can back out that information by looking at the distance and a star in the sky, and they use that to measure this kind of stuff. Well, we're not interested in this kind of scale. We're eventually going to try to measure things that are much better than that. And this gravity doesn't just change, it changes dynamically. And so up in the top corner here, you've got here variations of this. You can't hardly read this, but this is in microgal now, down in the sort of 20s. So we've gone down much finer scale. And these things are due to basically the ocean tides. So the water sloshing around on the planet changes the gravity field. And even that is not enough. If you go beyond that, you also get not just the ocean tides, which are sort of known pretty well from radar altimetry and so on, but you can also get non-tidal atmospheric and ocean variations. These are the ones that are shown here. For example, not only does the water flow around on the Earth, but the whole Earth actually has tides. So the Earth is actually moving as well as the oceans, but by a very small amount, and that amount is quite easily detectable, even with classical sensors. So people measuring gravity are really, really good at it. That's one of the messages that I want to get across. And in fact, you can go even beyond that, and this is where it starts to get really interesting. Remote sensing from space, you can actually see here that as you go through a large scan range from this GRACE mission, this is in microgal, so you're now getting down into a few parts. And so I want you to remember this number actually as we go on, this 10 to the minus 8. When you get down to measuring things in this range, you're starting to actually look at, if you look at this picture very carefully over time, you'll see that it's actually located on various sites where there are, for example, deserts. And you're actually starting to see things like the cloud patterns, the change in the gravity due to the motion of mass, like in the weather patterns around the Earth. So there's a great amount of interest from space measurements and looking at the mass changes on planet Earth for things like tectonic plates, for things like groundwater, and all that sort of thing. And so in the future, we would like to get even better at doing this sort of thing. And it's motivated not just by NASA, but by a number of organizations. There are lots of people who are very, very interested in measuring gravity fields. I'll mention a couple of other possible applications. Underwater navigation is an interesting thing because you can't really get GPS signals. GPS-free navigation in itself is interesting because the GPS system could potentially be blocked. Other things that you can do is you can fly satellites around, for example, asteroids or other small planets away from the Earth and by measuring the gravity field around them, learn information about the composition of those asteroids and so on. Okay, there's a long, long list of applications for measuring gravity. So what NASA's really interested in is trying to build up a functionality, and it comes partly from what we do in quantum physics, for using a quantum advantage to try to push this kind of remote sensing further and further on down this pathway towards higher and higher accuracy. And we're part of what's called a Quantum Pathways Institute in Gila. And this is what the work is that I'm going to talk about today. It's part of this collaboration. So we're kind of up here. We're building a device, which I'll show you about as I go on through the talk, to build a quantum sensor for this application. And we're part of a bigger team around the country that involves UC Santa Barbara, and they're involved in the sort of photonic integration, these little tiny laser integrated packages that could be used for a deployable system. We're involved with Texas, UT Austin, and with Caltech and with NIST in terms of like systems engineering to try to work out how you put all these pieces together and put them onto a spaceship, make it fly and do the right things that you expect. And the goal is really to try to use some of the ideas of quantum sensing, quantum physics, quantum metrology to build a kind of next generation device. So we're up here at the top. We're basically developing cold atom optical lattice-based interferometry techniques. So we're trying to build kind of the sensor, we're trying to build the device, and we're trying to understand what are the limitations and what we need to do in order to push this forward. Okay, so I'll just give you a brief background about what the idea is here. It's sort of motivated by the tremendous development in atomic clocks that have gone on over the past few decades. This picture on the left is the sort of time standard. This is like the NIST F1 cesium fountain clock. You use a cesium atom, you send it up, it goes up and down, goes through a microwave cavity twice, and you use Ramsey spectroscopy. So it's a standard kind of technique to read out the time of that atomic clock. And that forms the nation's time standard at the moment, although that will likely change. But there's been a couple of humongous developments in this field that have really pushed things on by orders of magnitude in terms of sensitivity. The first one is going from a microwave transition to an optical transition. It's work that was done, for example, on aluminum ion clocks. And then going further, putting these new kinds of optical transition systems, in particular using strontium and ytterbium, into optical lattices. And that's what I'm going to talk about today. So actually the best clocks in the world now which are orders of magnitude better than this, involve arrays of millions of fermionic atoms all stored in a crystal of light. And the fact that you can build the best clocks this way sort of shows that this is a pristine environment for precision measurements. It measures time extremely well. So if I look up here at the Allen deviation, this is kind of the characteristic plot that these people kind of look at all the time. This is averaging time here going out to 1,000, 10,000. And the Allen deviation tells you the sensitivity, fractional frequency sensitivity of your clock, 10 to the minus 16, 10 to the minus 17, 10 to the minus 18. The cesium clock is up here. A single iron clock is down here. And this best clock that I'm talking about is way down here. So you can see the order of magnitude improvements that have gone on due to this kind of facility. Over the last few decades, we've pushed down further and further down into the 10 to the minus 18 or even below. So this measures time, and the question we pose and want to answer is, can we measure space? In other words, instead of measuring temporal changes and measuring frequencies, making a frequency reference, what we would like to do is to measure inertial sensing. That is to measure the spatial forces, things like accelerations, rotations, the effects of gravity and so on our atoms. And we want to leverage the same kind of advances that's happened in clocks with large numbers, with long measurement times, and with precision metrology. So with that, let me explain how we go about measuring accelerations in using our quantum particles. A traditional atom interferometer kind of looks like this. You take an oven, you produce a beam of atoms spewing out of the oven, you collimate them, you form an atomic beam, and you take that beam and you pass it through a laser field. You pulse a laser light on it. And what can happen then, if you do it for just the right amount of interaction time, is it can have a 50-50 shot of absorbing a photon or not. And in this case, the light field's going from the bottom to the top. If it absorbs a photon, it gets a recoil kick, and the atom gets deflected. If it doesn't absorb a photon, it carries on. And this makes a beam splitter for atoms. So we divide our atomic beam up into two parts. It's not like each atom is going one way or the other. Each atom is going both ways, right? Because it's a superposition of taking both paths. Then we shine on light for twice the amount of time, and what that creates is a mirror where the atoms are reflected. And if they absorbed a photon, then they reflect back. If they didn't absorb, they absorb one, and that brings them into a closed path. And then if we carry on further, you can see that they recombine. And whether the atoms come out in one port or the other port now depends on the phase shift that they accumulate along these two different paths. And so by changing that phase shift, for example, by putting them in a gravity field, I can change the amount of flux in each of these ports. And that's the signal that an atomic interferometer measures. So it measures something that's to do with the difference in taking this path. If gravity is upwards, for example, they might go slower along this path than along this path. And they get a different phase when they do that in the matter wave. And so they get a different interference pattern. So we do this all the time when we try to measure things accurately. We make interferometers, just like that matter wave interferometer. I mean, this is the optical version of this, where you take a laser, you split it with a 50-50 beam splitter, you bring it back together, and then you measure the output flux on two photodiodes. That Mach-Zehnder interferometer is kind of the hallmark of precision measurements. You want to measure any distance accurately, you build an interferometer like this. The Bragg interferometer that I'm talking about is basically the same sort of thing. And what we want to do is to do that kind of thing in a lattice, where we split the atoms, we mirror them, and we bring them back together. So the question is, how can we go about doing this? And I'm going to show you that that's possible. I think it's not intuitively obvious that you could do that sort of thing in a crystal of light. And how do we do this? We need to make these analogs of optical components. So simple optical components is a beam splitter and a mirror. And how could we go about doing that? Well, we play a game. We use a kind of machine learning, which uses neural networks and our learning cycle to come up with a solution to designing quantum systems to do what you want with them. What I'm going to show you now can be applied to this problem, but it can be applied to lots of problems in quantum physics. And the basic idea is that behind reinforcement learning is it's motivated by people who work in things like teaching robots to walk. They do reinforcement learning. They'll they'll take a robot which falls over all the time, and it has to work out how to move its limbs and its arms and its legs and its knees, how to manipulate all these joints, and it keeps on doing random stuff, hopefully not too much random stuff to break, but it keeps on trying and trying and trying, and eventually it'll take a step, and then the computer will decide that was a good sequence of actions to take to move you from one step to the next, and it will eventually learn how to walk. I would say humans do this too. You see babies, like they get up, they fall over, they get up, they fall over, finally they get up and they take a step, right? So we do this all the time. And the question is, can we use that kind of reinforcement learning to teach our quantum systems to do a sort of target operation? And it looks like this. You have an agent like this, which is encapsulated by a neural net. Basically, it's going to come up with an action. The action might be to move a lattice, say from left to right or up or down or in or out. We can then carry out that action either in an experiment or by solving an equation on a computer that responds to that input for our system. And then we can decide, was that a good action or not, by computing the reward. After many, many cycles around this, we want to be able to produce a target device. We want to say, we produced a beam splitter or we produced a mirror. And so our typical thing is to go around this cycle many, many times. Basically, the agent says, do this action. Oh, this is my reward. Do this action. This is my reward. And eventually it decides that it's come up with a good protocol for learning how to do a quantum design problem. So the components that are in here is the agent. The agent is a computer program. There's the environment. The environment is also perhaps a computer program, or it's perhaps an experiment. You can also learn off the experiment. And the goal is to find a sequence of actions that maximizes the long-term rewards, sort of allows you to win the game, to take a step, or if you're playing chess, to checkmate the opponent, or if you're playing Go, I don't know what you have to do. You have to make a pattern or something, right, where the tiles go across the board or something like that. I don't know, however you win Go. Anyway, that's the general idea, okay? So we do that. We actually have two ways of doing this. One of which is based on machine learning like this, going around a learning cycle like this with reinforcement learning. There are also ways of coming up with solutions for this in applied mathematics or in engineering sciences, where they use things like quantum optimal control. And they use those for things like making helicopters stable, or making motorcycles stable, controlling systems in airplanes. Just a whole host of problems can be solved like this. And this is sort of their learning cycle. I'm not going to go into the details of this, but it basically involves solving a differential equation where you look at a trajectory and you sort of locally optimize using a Newtonian minimization algorithm. And then you end up typically with a solution which isn't consistent with the evolution of the Schrodinger equation anymore, and you have to do a kind of projection operator, and then you can go around and relearn this and sort of to use a kind of like gradient descent, falling down the hill the fastest way to find the global minimum, the optimization. What I've got up here are two actual solutions from these different methods for a beam splitter. And this corresponds to a plot of the position of an optical lattice as a function of time. Both of these produce beam splitter with 99-point-something% fidelity. So they divide an atom cloud up into two pieces, just like the atomic beam. When I originally showed you a matter wave interferometer with pulses of light, we can do the same thing by moving an optical lattice with extremely strange patterns. This is some weird oscillating solution for reinforcement learning. But look at this one. This is completely crazy. The lattice moves over here, it moves, and then suddenly zips over here, moves back, and then doesn't do anything for a while, and then, okay, it zips back and forward, and that pattern of motion corresponds to a beam splitter. So part of this story here is that these are crazy. Like, you wouldn't intuit, that something like this is the solution to this quantum design problem. But computers can find these needle in a haystack solutions extremely well. Okay, so with that background, let me show you a little bit about experiments. So we have a rubidium-87 experiment that can produce BEC atoms. We start off here with a 3D rubidium MOT. And so you're looking here at about 10 to the 9 rubidium atoms. They form a big cloud that you can see with your eye if you turn down lights and things like that. It's very easy to see. These atoms are at about 300 microkelvin. It kind of forms the starting point of the experiment. And then we undergo a series of subdoppler cooling steps. We use what's called polarization gradient cooling and compressed MOT and gray molasses. And all this does is to shrink that cloud down into a very small ball and lower the temperature down to about 20 microkelvin. And then we load these into basically a pair of, like an optical tweezer. It's a cross dipole trap. So the light actually goes through the atoms with a color that attracts the atoms. And then it goes around a loop and goes back through the cloud again and forms a cross. And where the light beams cross, the atoms see a potential well and they get stuck. And you can actually see this when we firstly load the atoms from this MOT. You can see them basically in the middle, and they're also spilling out along the laser beams as they cross. And at that point, we have about 3 million atoms. And then you can slowly turn down the intensity of these lasers. Actually, we can't see these lasers. They're 1064 nanometers, so they're invisible, infrared. As you slowly lower the intensity, though, the hot atoms boil away, and you undergo forced evaporative cooling. And so you end up down here with a very small, cold, dense cloud. If you do this just right and get the collisions happening fast enough, you can form a Bose-Einstein condensate, and we do that all day, every day. We produce condensates probably every 10, 15 seconds, and we literally can go in the morning, turn the experiment on, run all day, and then go home at 3 a.m. or whatever you do. Yeah, so this is a picture of BEC formation here. You can see here the cloud getting colder and denser, and there's a central spike. I think I blame Eric Cornell for having to make these images, but everybody has to make the classic 3 images above, during, and after BEC formation. So we have about a BEC temperature is below 20 nanokelvin. It gets really hard to measure temperature in this region. So basically for all purposes of this talk, it's 0 temperature, and we can produce condensates of maybe 200,000 atoms in tens of seconds. And what's interesting about this all-optical approach to making BEC with just laser beams is that it's completely agnostic to the magnetic field. Anytime we have a magnetic field is up here, these coils are part of the MOT system, but after that they're turned off, okay? So everything I'm going to talk about today doesn't depend on the spin of the atoms, and that's extremely important for precision measurements because it's hard to shield completely the magnetic field. So if you want to measure things very accurately, that's a big advantage. Well, going back a couple of years, we had an original experiment. You won't take much away from this. I'll show you a little bit more about the elements that are inside this. Perhaps a schematic like this might help. You have a little cell in the middle, which is about 1 inch on the side. It's just air around the outside, but inside there, it's a very, very good vacuum. And the lifetime of the atoms in there is hundreds of seconds. So you basically have no air and no thermal contact in the middle. You form the BEC right in the middle where it's isolated from the environment completely. And then we can create the cross dipole trap, which you can see on here. And we can also load these things into a one-dimensional optical lattice. And that's what I called the crystal of light at the beginning of the talk. We're basically going to shine 2 laser beams at each other with the same frequency, and they're going to form a standing wave of light in such a way that the atoms are going to be attracted to the regions of low or high intensity in the lattice. And then we can see what the atoms are doing by shining a resonant beam, which is 780 nanometers, and looking at the absorption image of those atoms onto a CMOS camera here. And we're going to see some of those absorption images in just a minute. So we did that experiment, but what I'm going to show you actually is that in August, we cleared the table, okay? So this is what the laser table looked like last August. There is no optics on here. All we have here is the middle. This is the little cell in which the condensate is formed. There's one a little bit below this breadboard and a little bit above here, and everything else is cleared off. And why did we do that? Well, we wanted to move from a 1D experiment to a 3D experiment, but we also wanted to build an environmental control box around the experiment so that we can control the temperature extremely well. So this is day 0 here, and these guys working in the lab are pretty good, okay? So I take no credit for this. This is day 7 here, and they had already made a BEC after 7 days. And I think that must be just a kind of record. To go from nothing to BEC in 7 days, I think it should be in the Guinness Book of Records. So pretty impressed. So they could make these, all the stuff that I've talked about was put on the laser table in 1 week. And when we take data, we take it up here on the top of the table. So you can see up here that that's how we normally function when we're taking measurements. That's Katie. No. Actually, it's really good to have someone who's kind of small so they can reach in there and put that BNC cable in the place where you should have put it before. This is the environmental control box. We close all this up. It's got HEPA filters. It's got an active control system, and we have chilled water, which we flow into the end of this table. And we can control the temperature down to about 0.1 degrees. Anyway, this is the experiment, which I'll be describing. It's very compact. It sits on the end of a laser table. Probably it would fit in a cubic meter size box, so I'm not going to say this is deployable for a space purpose yet, but most of this can be miniaturized much further, and I think we have a clear pathway to doing that. The actual core part of the science system is sitting right in the middle, where you probably can't really see here, but I'll describe a couple of the components. The MOT part of this is very standard laser cooling technology. What's not so standard, this is a 50-watt IPG laser at 1064, and that's producing the cross dipole. So with these optics, it goes through the cell and it comes back and goes through the cell again, so it passes through twice, makes the cross, and with an AOM we decrease its intensity, doing the forced evaporation. And on the top up here, pointing at you, is another IPG laser, and that creates all of the beams for the lattice. And so we're going to create a 3D lattice here. We have 6 laser beams all shining at each other. There's no retroreflection going on. This is not a simple experiment, because every one of those laser beams has to be controlled in its frequency. And that's because when you have a lattice formed by 2 interfering laser beams, if you shift one of the laser beams up in frequency and the other one down in frequency, you form a standing wave pattern, but the standing wave pattern walks one way or the other. If you change the frequencies, so the other one's higher and this one's lower, the atom walks back in the other direction. So we can make the atom walk in any direction in 3 dimensions we want by controlling very carefully the frequencies of all of the 6 laser beams that are produced by this. So that's hard to see, but maybe it's easier to visualize if I give you a schematic. Right in the middle of that experiment is this cell, which has got a very, very good vacuum in it. And you can see the 6 beams coming in from all the different Cartesian directions. In the vertical direction, we come down, but there's no way we can come up because that's got no optical access. And so we have a small integrated optic in here, a little mirror at 4 degrees. And so this 8-degree angle here is enough to make it miss the cloud. And that's how we make the lattice in the vertical direction. What's actually going on there in that interaction region is we have a crystal of light, and the atoms are stored in that crystal in the places where the intensity peaks and valleys. And so you can see here sort of a visualization of that. That's going to be going on in the experiment. The spacing between these cells is given by the wavelength of light. It's equal to lambda upon 2 is the distance between adjacent lattice sites. And so we make this crystal. So what is it that we're going to do our interferometry with? Well, it's block interferometry. So our Hamiltonian, if we just have a lattice in 1 dimension, you can see here that we get an interference pattern. We have a Hamiltonian with the atoms. They have kinetic energy and they have potential energy. Potential energy has an interference of cosine 2kx. It's just a standing wave when you shine 2 laser beams at each other with wave vector k. And then we're going to make them walk left and walk right with a function which shifts that interference pattern called phi of t. In doing that, what we want to do is to manipulate the atoms amongst the energy bands of an optical lattice. And this is a solid state physics problem. So we end up with energy bands, and we can talk about those just like an analogy with a solid state material. In particular, we have these lowest bands, and then we have upper bands here with slight avoided crossings. What do these bands look like in terms of the momentum of the atoms? The lowest band, 0 here, is basically atoms in the 0 momentum state, which is just like a normal Bose-Einstein condensate, where the atoms are stopped. They're just like 0 momentum. And there's just a little bit of plus and minus 2 h bar k. Why h bar k? Because the lattice has a spacing of lambda upon 2. So in the reciprocal space, momentum is always going to be discrete. And it's discrete in units of 2h bar k. You can think about that as the fact that an atom, if it absorbs a photon, it gets a recoil of h bar k. And when it emits that photon, if it emits it in the opposite direction, it gets another h bar k. It can only make transitions of 2h bar k in all different dimensions. And so it always looks like this. This is the first excited state, the second. And then by the time we get up to the third excited state, what you see here is plus and minus 4h bar k. And you know, this thing looks like a beam splitter. This corresponds to atoms going left and atoms going right with an equal superposition. So you can sort of get the idea. To build beam splitters, what we need to do is to make transitions between block states. For example, going from 0 up to 3 would take us from basically 0 momentum into a superposition of going left and right. And that's exactly what we do in optics when we put things through a half-silvered mirror. 4 is also the same, but that is a different parity. This is plus plus, this is plus minus. I'll come back to that in a little bit. So you can see down here that we've got a division of two parts. This is the depth of the lattice for this calculation. These three states are what we call the valence band, and these are called the conduction band. In the valence band, the atoms can't move because they're locked in the lattice sites, and in the conduction band, they have enough energy to ripple across the surface of the lattice and go for large distances. So we want to do these transitions by this control parameter. And this is just to show you a typical example. When we load the condensate and we turn on the lattice, you can see it agrees really well, the density distribution, with what you would expect for theory. Okay, so how do we measure the momentum? We just turn the whole lattice off, and then we've got this like crystal of light, and then the atoms are just going to freely diffract with time of flight. And then what we're going to see is the far field of the diffraction pattern. And since it's lambda upon 2 spacing, we're going to see 2h bar k splittings in the diffraction pattern. And we just count the atoms in each blob. No, we have to so if we just turn off the lattice, we see that. How do we make it go from 0 to 3 to this plus and minus 4? Well, we have to use our machine learning to design the control function.
In the lattice will have different momenta. Is that the lattice constants, like the formation of the lattice is different, or you turn off the lattice?
So we can apply a shaking function with the lattice, and we can hold it fixed there, and then the atoms will just slowly spread across. And if we drop the atoms, we'll see two blobs. You can see it directly. We can actually do in situ imaging. We can watch the atoms move. Okay. So we can do this. Here's 1D. We can also do it in 2D by using 2 of our lattice directions. And we can do it in 3D by using all 3 of our lattice directions. So you actually form a far field interference pattern, which can be 1-dimensional, 2-dimensional, or 3-dimensional. Okay, so we can do this whole problem along any Cartesian axis, or all axes at once. So this is just time of flight images. These actually do look a lot better than this. So it's somewhat degraded by your projector, I'm afraid. So don't blame me. You know, the images on our camera look somewhat better. Okay, atoms are multidimensional lattices. So I just talked about this. One thing I'll just really briefly mention, I don't want us to spend time on this, but you can ramp the lattice up slowly. When it's very, very weak, you have a condensate, and the atoms are all phase coherent throughout the entire 3 dimensions. They basically can talk to each other by tunneling through the lattice a little bit. At some point, though, the lattice gets so deep that the atoms in consecutive sites lose communication with each other, and you undergo a quantum phase transition to what's called a Mott insulator state. And we see that directly. This insulator state occurs around here. And after that point, what we see when we expand the cloud is that you don't have no longer a diffraction pattern. You don't see this. And that superfluid Mott insulator transition is itself really interesting. Actually, there's a lot of interesting condensed matter physics that you can study in this problem, which I'm not going to touch on today. You can study, for example, block oscillations. These occur in principle in solid state systems, although most materials have too many imperfections to see well. But we can easily do this. We can easily study these. Can you even see these things? No. That is really unfortunate. I think gray does not come through at all. Well, all I'm going to say is if you take a system of atoms in an optical lattice and you try to apply a force to them, you might think that they get accelerated and fall out of the lattice, but that's actually not what happens in quantum mechanics. What happens is they have to move within the Brougham zone in the lattice solid state theory, and they get accelerated until they hit the edge of the Brougham zone, and then they undergo what's called Bragg reflection, which is a mirror for the atoms. So with perfect fidelity. They get reflected and go the other way. So they end up going, accelerating a little bit, getting reflected, accelerating a little bit, getting reflected. And these things are called block oscillations. And we can see those very easily by accelerating our lattice. As I said, we have frequency control of the lattice, so we can accelerate the lattice under the atoms, and we can see block oscillations persist for extremely long times. In fact, we can do not only block oscillations in 1D, which other people have studied before us extensively, but we can also see these things in 2 dimensions by accelerating the lattice at once in both dimensions. And the frequencies of these oscillations actually provide a measurement of the force or measurement of the acceleration, and this forms a vector accelerometer, which is actually in itself quite interesting. We're just fitting here in both directions, x and y, 2-dimensional block oscillations, and we applied an acceleration of 2g, and then you can see we can pull out of the fits a very good measurement of what's happening. So you could use this as a sensor. You could use this as a vector accelerometer in a deployable system. Anyway, I'm not going to concentrate on this. I wanted to show you mostly our work on atom interferometry. So one of the interesting things about this machine learning approach, rather than these kind of light pulses and so on, is that when you do the sort of standard version of atom interferometry with pi upon 2 pi, pi upon 2 pulses, you have a fixed geometry. You build a tube, you have an atom beam going through it, and you build these things in certain interaction regions. So your geometry is fixed by your design, your hardware. But you can see from what I'm doing here that we're able to build components by machine learning that just move the lattice around, and we can apply those to waveform generators in the lab and run multiple different types of programs on the same apparatus. So we have the ability to make this device flexible. Like one day it might be an accelerometer, the next day it might be a gyroscope. And we don't have to change any of the hardware, which is something that's extremely unique in this field. And we can program it to be good at being an accelerometer, but being insensitive to something that is what's called a nuisance parameter. So for example, we might not be able to control the lattice depth very well. We can come up with machine learned solutions that are agnostic to the lattice depth. And those sort of things are relatively easy to build into reinforcement learning. And we can build devices that have never existed. You can build multi-dimensional accelerometers. You can also build multi-axis gyroscopes, gravity gradiometers that measure all the tensor elements of the gravity field. There are things that we can build out in this lattice system that no one has ever been able to do in inertial sensing before. Basically, anything that you want to do in this relies on a very good experiment in a controllable 2D or 3D lattice. So let me show you some results. Let's see some data. So with all that background here is a interferometer. Okay, so what you're looking at here is the position of the lattice, 5t as a function of time. This first wacky thing here is what I showed you earlier, and I called a beam splitter. You apply this to a waveform generator, it beam splits a condensate. Here's another device that's been learned. This is a unitary transformation, which corresponds to a mirror that reflects atoms. Atoms going left end up going right, atoms that are going right end up going left. This one here is the time reverse of this, which forms a recombiner. Much like in a Mach-Zehnder interferometer, you have another mirror at the end of the sequence. And so all of these images that look like this blue, these are all experimental, okay? These are direct images taken on a CMOS camera of the absorption pattern of the cloud after letting it expand. And you can see here that we start off with a condensate, which I described before, the 0 state. And then after we apply this, we end up with something that looks very, very much like that 3 state, which is the beam split state with plus and minus 4 h bar k. After the mirror, this one goes to here and this one goes to here. So you can't really see them swap, but they really do swap. In fact, we can make them all go here and we can see this cloud go to this one. And we can make them all go here and we can see this one go to this one. So this mirror works really well with high fidelity as well. And then the time reversal, you can see, after all this craziness of the lattice position, we are almost exactly back in the condensate, the original condensate wave function again, which to my eye is absolutely incredible. You do this crazy stuff, doing this manipulation of the condensate atoms, and you can see the purity with which we are able to produce this result. So a interferometer, when you don't have a signal, should always look like this. You start with an initial state, it does its thing, but if the path difference is exactly the same, it should always end up in the state that you started with. Like an interferometer with no signal is an identity operator. And so you can see we do that with high fidelity. We can do it by applying this along the x and z directions at once. And then we're going to split the atoms and we're going to split them again. So they're going to go off in 4 different directions in a kind of multi-axis version of a Mach-Zehnder. And then we're going to mirror them and we're going to bring them back together. In this case here, we have an interferometer, but it has, instead of like 2 ports like a normal interferometer, here's our diffraction image with all these H bar Ks, and we have something like 49 output ports. So part of the goal now is going to be, how do we extract the signal out of such a multi-output interferometer system? So this kind of gives you a visualization of what's going on. We start off with the condensate in the lattice, we split it into 2 different paths, we form a mirror, we recombine them, and the atoms come together. And we can change the amount of propagation as we wait for longer. Once they're in the conduction band, they can ripple along the lattice for different distances. In 2D, they're kind of splitting in a square pattern. They're going out and along 4 axes, and we're mirroring them. They're all coming back together. And in the resulting cloud that we form, we can then expand it, and we can look at the diffraction pattern, and we can look at the amount of population in all of these 49 output ports, and try to ask about what kinds of inertial signals is this accelerometer seeing. So this is showing you raw images directly off the screen. And what we're doing here is we are applying a signal now. We are slowly ramping the lattice in 2 different dimensions in the X and Z direction by equal magnitude. And we're starting at the beginning of the cycle here at -0.2, -0.2, and we're going to +0.2, +0.2. And as we slowly sweep through the amount of, these are all individual experiments, you can sort of see the pattern going from the bottom left corner to the top right corner. So each one of these images is a fingerprint, and we can extract from that fingerprint what the value of the acceleration is along 2 different dimensions at once. This is called a multi-axis accelerometer, which is something that people have been trying to build in atomic interferometry for a long time. It's not easy to do in a traditional light pulse system, and there are some works on it, but you know, this is a different kind of solution to this problem. And just to show you how good this can be, here is a plot of -0.2 to +0.2. As we go through this with the same acceleration in both the X and Y, you can see the different fingerprint patterns that we get. And the idea is to extract from these images what is the value of the acceleration that we applied. So what we can do is we can take these images and we can kind of sum them up along this direction and sum them up along this direction. And we can look at how those sums vary as we move along this line. And we can form a kind of a calibration chart of all of the different momentum components and along either the X or Z direction. That's what this is here. So these are the different output ports, 0 H bar K, 2 H bar K, 4 H bar K, 6 H bar K, down to -6 H bar K. So there's 7 different curves here. And each one of these curves here tells you something about what values of the population you expect at each different acceleration from -0.2 G to +0.2 G in the 2 different dimensions. So if I give you an arbitrary image, you can come along and match it to those calibration charts and give me a predicted value with uncertainty about what the value of the parameter is. So if we take those images that I showed you there, and we did 41 experiments, you can see here the values of the reconstructed X and Y accelerations with error bars, and it agrees incredibly well with what we applied. So this is just to show you that the system can be used to measure a multi-axis acceleration. And it's really a vector acceleration. You can measure just not the magnitude. Here we do a number of experiments, 40 experiments going around a circle. In other words, we keep the value of the acceleration vector constant, but we change the direction of the acceleration in the XY plane. And you can see the patterns changing as we go around the circle, but we can be quantitative about this. We can evaluate for each one of these images the distribution of X and Z momenta, and we can use a least squares fit against our calibration chart. And in this case, what we did is we referenced it against the acceleration chart for the previous experiments. So there's no circular arguments going on here. This is with our fixed model. We reference this against the model, and we reconstruct what the values of the acceleration we applied. And you can see we really do have a multi-axis accelerometer with this kinds of system. So as I said, there are people that are really interested in doing this kind of inertial sensing with quantum systems. And here is a simple example that it works. One thing you can do here is what's called Bayesian reconstruction. And what I mean by that is if you have a certain value of acceleration, and this value of acceleration is what this thing converges to, so we applied this in the experiment, you can just sit there taking more and more data. And what Bayesian reconstruction is it updates your posterior, your information about the probability distribution as you accumulate more data. And you can see here, even though these images are noisy, as we accumulate more and more data, the system rapidly converges on a fixed value of the acceleration. And that's how the sensor would work in practice. That's the kind of things that people would do in the field. What you're mostly interested in is not just does it work, but like how good is the system. So let me just say a few words now about sensitivity and where we're going to go with this kind of device. So what we did here is we took a certain value of the acceleration, and you can see these things converging. I'll explain this in just a sec. But we just took one value of the acceleration for the two different dimensions, and we just sat there repeating experiments again and again and again and again to look at how this system averages down. And this is the way, people who do precision measurements look at the sensitivity of their device and the short-term and long-term stabilities. So you can sort of see that over here. We've got a plot here of the sensitivity. This is the uncertainty in the acceleration in G as we accumulate more and more data. These data are shown down here, which is called shot number. And remember, every one of these shots, every run of the experiment is using 30,000 condensate atoms or something like that. Some number that we fixed in the experiment. So as we accumulate more data and reconstruct the value of the z acceleration and the x acceleration, which it's a multi-axis sensor, so we get two lines here, you can see it averaging down. And then after we take, say, 100 shots, we're down 10 to the minus 4g or something. So I'll comment on that just in a sec. But another thing you can do is you can take many examples from your 200 pool of 3 experiments or of 15 experiments or of 100 experiments. And as you histogram those predicted accelerations, what you see is something which is a distribution which gets narrower and narrower and narrower and agrees with this uncertainty that you get from the reconstruction. So this thing is going down, and it goes down in a way that's easy to understand. This slope here is actually fixed on a log-log scale because this is just statistical averaging, and when you statistically average independent variables, it goes down as the 1 divided by the square root of n. So that gradient is actually a gradient of a half. And so all of these kind of systematic plots will look like this. The actual values here, you can see this is on a log linear scale of the acceleration values that it's getting. This is the uncertainty, this is the mean value, and you see it converging towards a specific predicted value. And that corresponds to this fingerprint that we see for the value of acceleration that we applied. Okay, so you might think, well, that's working, but this number is not that interesting. 10 to the minus 4g is not very good. But this was done without any propagation time in the accelerometer at all, okay? So this is a tiny accelerometer. It's about a few microns in scale. So the atoms are just splitting just a tiny little bit and coming back together. So the enclosed area in space-time is really small, and this is consistent with what we expect for this. So what we're showing you here is a proof of principle. Just this is how it works. But the question is, how far can you actually go with this? Is it a technologically useful device? You can measure different values of the acceleration in this kind of proof of principle. So, instead of that specific one, here's 0.02, 0.16, here's 0, 0, 0.1, 0.05, minus 0.2, 0.1. Different values of the vector acceleration will correspond to different patterns. But for all of these patterns, you can see we average down as the square root of n. And some are slightly more sensitive than others, some are slightly less sensitive. And that's to do with the quantum mechanics of wave packet dynamics in the lattice. But nevertheless, it can be done. This is a multi-axis sensor. So more recently, we started to look at longer accelerometers because we want to split the atoms by further, enclose more area, and get a more sensitive measurement device. This is a much longer. That first one there was only for a few hundred microseconds. This is 5 milliseconds, okay? And in this case, the atoms are moving about 80 microns, or about 160 lattice sites before they come back together. And as we start to do that, you see here that the range of accelerations that we need to apply to see a signal has gone down heaps. We're now going down from sort of 10 to the minus 3 G range, and you can see here we still have very, very good contrast of all of these fringes. And so from that fingerprint pattern, we can now accurately work out what the acceleration that we apply is. So for example, we applied 0.0008 g. And in 5 milliseconds, when you apply such a small acceleration, you're measuring a lattice which is moving by a tiny fraction of a single lattice site. It's hardly moving, and yet you can still get really high fringes out of the matter wave interferometry. So it converges after 100 shots of this, reruns of this experiment on the value that we apply. And here is the sensitivity uncertainty as we start to accumulate more data up to 100 shots. And now we're getting down into the 10 to the minus 6 or milligal kind of range. And you can see we're starting to talk about the numbers that I showed you right at the beginning of the experiment in those plots that came from Grace. So it's kind of getting interesting, right? And this is from the spring of this year. As I said, we only started building this in August, so don't hold me, to task for doing everything yet. We're working on this hard. More recently, we've been working a lot on stabilizing the system, removing all the noise sources, and allowing us to go to longer and longer propagation times. This is, I'm going to say preliminary, as in like data taken last night, or maybe the night before, or last week actually, but so very, very recent. But I'm just going to give you a sort of whet your appetite a little bit for where this sort of experiment could easily go. This is now 20 milliseconds in a 1D lattice. Now 20 milliseconds, this is an extraordinarily long time. The atoms are now propagating for about 370 micrometers. That is like 700 odd lattice sites. So this is really a macroscopic distance. You can almost imagine putting a physical object in here. This is a coherent superposition of atoms, huge distance apart. And we're now applying plus or minus 10 to the minus 4G signals, and you can see you can split this line. We've got extremely good contrast still in our interference fringes. This is actually just to show you what we look at in the lab. These are the raw images, and you can see the fringing quite clearly as we cascade different runs of the experiment next to each other. And it's that fringing that we're actually measuring in terms of the output. So if we look at what's called the classical Fisher information associated with this, that is how sensitive this thing actually is, we can calculate how this thing averages down. And so I don't know if you can read this because it's kind of crummy, but this is 10 to the minus 6 going down to 10 to the minus 8. And you can see here that as we go out of sort of shot numbers, we're running experiments every 10 seconds or so. Over reasonable times, we're going to get down into these numbers, which are actually pretty interesting for the purposes of this experiment. We don't know how far we can push this yet, but we've already got over just this last year into a regime that is intriguing, is what I will say. Okay, so this is not actual published work yet, but we know we have the fundamental sensitivity in this device. Okay, with that, I'm going to end and take questions, but let me just say a few closing remarks here. We've got a long way to go in this, improving accuracy, sensitivity, making the thing more stable, moving more into the realm of a precision measurement experiment. We're building up new experiments with rubidium and strontium, and we really want to understand a whole lot more to do with the different dimensionality, the different kinds of devices that we can make. I showed you superfluid mod insulator. There are many other things that we could work. We can keep on working on our machine design, our machine learning. That's a whole field of research in its own right, I would argue. And there's a lot of work that could be done on that in terms of theory research. We're going to do a lot of work, more work on experimental improvements, making BECs better, making them faster, making them more stable. There's a lot of things that we need to do along those lines. Removing technical noise and servoing out noise sources that are important to the interferometry. And we're going to do a lot of things on deployability. Size, weight, and power, or SWAP, is important for space-based applications. And all the things to do with stability and the different kinds of sensors that we can build, gyroscopes, gravity gradiometers. We know how to build all these things, but we haven't had time yet to demonstrate them all in the lab. So with that, I'll thank you for your attention.
Right.
How often do you think this would need to be recalibrated if made in a commercial device?
Yeah, so calibration is actually really interesting because that is a huge problem for classical sensors. When you build a gyroscope, you know, one of the things that quantum brings to the game is long-term stability. You know, in other words, when I run my 1064 laser, it is a very narrow line with stable laser, and it produces, especially when we servo and lock the laser system, what we're doing in the lab now, it produces the same interference pattern every time. So long-term stability is one of the huge selling points for quantum systems in this world. And so, you know, in other words, I don't think we need to recalibrate. There are obviously things that need to be done. The lasers have to remain locked. There are things that have to be done all the time to keep the experiment running. But the fundamental laws of quantum never change. Okay, so I'm going to argue that's a glass half full problem. You know?
Yeah, so it was really great talk. Thank you. How do you know if there is a solution through the reinforcement learning in your physics experiment? I guess it depends on the problem set.
No, it's a great question, and I think so I can tell you is what we see, and I don't think we knew this before we did this, but if I set up this problem to design a beam splitter, it takes me a few minutes. Okay, I can just run it. 5 minutes later, I have a new beam splitter. I can put it into the waveform generator in the lab. We can run it. It'll work. Okay, we've done this many times. Every time I run it, I see a different beam splitter. Okay, never the same. It's always some other solution, and what the classes of these solutions, what the statistics of these solutions are, I don't know, but there's definitely a complicated landscape. It has many different possible answers. But what I think happens is that as I take the terminal time down, is I tell it that you've only got this amount of time to run your beam splitter and go this amount of time. Eventually, the time is too short for the atoms to actually receive an impulse forced by the lattice, and the solutions disappear. And they disappear by having not being able to find a 99% fidelity solution anymore. Eventually, I can only find a 70% solution, and so that cutoff is due to physics. I mean, it must be the way, and we see that. Okay, but yeah, there's a lot of complexity to the machine design.
You said you did a CFI analysis on your setup. Do you have a QFI analysis also?
Yeah.
How much better can you possibly get?
You know, the QFI is super interesting because what actually happens is when you look at how, if you ask a system, just a general system, to design a beam splitter using machine learning, and you look at the QFI and CFI go as a function of time. What it does is the QFI and CFI sort of diverge actually at the beginning. If I pick a sort of minimum basis, the QFI it starts out by trying to find a solution in which the quantum Fisher information is as good as possible, but that's not directly measurable because I need to work out what basis that goes into. But if I have a certain measurement basis like momentum like this, that's typically not the right basis, and it tends to have a really crummy response. And then right at the end of the machine learning, it will say, what you need to do is shape in this way to convert your great QFI into CFI that can be actually measured in the lab, and CFI lock it up to all the value that the QFI produces. So the computer knows actually about what's going on in terms of CFI, QFI, and you can actually see that in the learning cycle. So it's hard for me to explain in 2 minutes, but it's really an interesting problem. So somewhere hidden behind the neural net is knowledge about what the quantum, some of the things that we understand about quantum physics.
Thank you for the talk. I don't know if this question really makes sense, but my understanding from these accelerometry measurements, you're kind of observing the evolution of the block oscillations. So I was wondering if you modulate the lattice spacing, whether that gives you maybe like sensitivity improvement by having maybe some kind of like feeding going on in the block oscillation.
Yeah, so you can do this with block oscillations, and you can use block oscillations to accelerate the atoms differentially even more, so they split faster. But what we're doing here in the interferometry is not block oscillation. Okay, the difference is Bloch oscillations occur in the ground state of the lattice, and they correspond to going around the Brougham zone in the last band. In our case, what we're doing is we're going from the last band, which I call the valence band, and we're putting atoms through machine learning into the conduction band, where they have energies that is actually above the lattice potential. Even classically, the marbles would roll across the hills and go out. So that's why they go out. And our interferometry comes from what you can understand from a path integral formulation. Basically, the atoms and the matter wave components accumulate a phase along these paths. And when they come back together, you've got to compare these phases to decide if it was constructive or destructive interference. And that path sensitivity depends on the area that you enclose in space-time. So this sort of thing is understood in all forms of atom interferometry. It comes from de Broglie matter waves. It's something that goes back 100 years, you know, and so that's all we're doing. We're splitting the matter wave up into two pieces, bringing them back together, and then right at the end we put them back into the valence band where we generate the quantum interference that generates the signal. Okay, does that make sense? I'm sorry. You do.
Go ahead.
Yes. What are the typical error sources other than the temperature?
Okay, so error sources. First of all, I'd say if our beam filters and mirrors and so on are not 100% fidelity, we really don't care. Okay, because what happens is we get some atoms that instead of having plus or minus 4 h bar k, they have plus 8 h bar k, and they zip off to infinity, and they just, I don't care. You know, they don't enter our signal. The sort of things that are really problematic are phase diffusion of the lattice. So if our lattice beams have some differential frequency noise, then the standing wave will walk in a way that we don't know. And that's actually indistinguishable from our signal. That's a big problem. That's why we spend so much time surveying the lattice and trying to lock it in place. We've spent like the last year basically working on that problem. It's not trivial. Okay? So that's one sequence of noise. The other one I'll say that's really important is interaction effects. So condensates have mean fields, and if you put a lot of atoms in this component and a few atoms in this component, then these atoms will have a higher energy than these atoms. They have a different chemical potential, so they accumulate phase at a different rate, and that's also indistinguishable from our signal. So we're working really hard to control these things.
One last question.
So one of your sensitivity versus averaging plots, it seemed as if the 1/squared time scaling took a little bit of time to kick in.
I think I know what you mean. Which one are you talking about?
Yeah.
Say that one.
Yeah. So
Are you talking about like what happens
yeah,
here?
what's happening? Sure.
So, okay, this one point really in. This converges on the prediction that you get from the classical Fisher information, which you may or may not know. I don't know. It's also the Kramer-Rao bound. These kinds of statistical things are what you get after a large number of measurements. Basically, when the central limit theorem kicks in. When you're talking about the first few measurements, 1, 2, 3, things like this, you have a bimodal distribution. You have many kind of hypotheses which are consistent with the data. Okay, so there's no way that you know what it is. And then when you go and calculate the standard deviation of a bimodal distribution, you get something crazy. So it's typical. This is kind of the Bayesian regime, and it's not until you get down here that you get into the CFI regime.
Right, let's sign for you again.